So hey everyone, welcome back to my channel. My name is Tanuj. So from this video on, I'm going to start a new series on DSA. Okay, so I'll be starting from the basics and going all the way up to problem solving and algorithms as well. So in this video, I'm just going to explain you what exactly is the time and space complexity, and then from there we'll just go on to other concepts as well that we need to know as a developer about all the concepts about DSA. Okay, so I'll be covering all of them one by one in a sequence. Okay, so I'm just going to get started with time complexity. Okay, so let's understand what exactly is time complexity. So by definition, you see that time complexity is nothing but the time taken by an algorithm or a function based on the input size. Okay, so the keywords here are the time complexity, the algorithm or function, and the input size. So these three terms over here. Okay, so and these are all denoted in big O notation. Okay, so we say that the time complexity of certain function or an algorithm is O of something. Okay, so I'll just come to that what it is. So it is we just need to keep in mind that it is something that a time should be taken, and also I'll come to space complexity. What is that? So let us first understand what is time complexity, and it is denoted by big O notation, as I told. So there are different types of time complexity. Okay, so these are the most commonly faced time complexities, okay, with any kind of function or algorithm that we perform. So one is the constant time, and then is the linear time, quadratic time, and the logarithmic time. Okay, so these are the four main concepts that you need to know when it comes to time complexity, and I'm going to explain you what exactly is one by one. So based on the input size, okay, so the term I used, input size, will denote which of these time complexity it falls under. Okay, so let's say I have an array over here, A, B, C and D. Okay, so what is the constant time? For example, if I want to access what is the element at index 1. Okay, so what is the index 1? So index are 0 based in array, so we calculate from 0 1. So what is the value over here? That is B, right? So we return B itself. So if I just say this array and pass in the index 1, so we get B as the element, right? So what is the time taken by this? So do I have to loop across all the elements to get this particular element? No, right? So I just go to the index and just see what is there, and I get the element, it's there in there itself, right? So what is this called? So this is the constant time. Okay, so how many ever elements are there? So even if I have all the 26 alphabets in this array, so based on the index which I specify, I get that element. Okay, so I just go to the index, find the value, and then use that. Okay, so this is the example for constant time. So if I draw the graph to denote the constant time, where if I just say the x-axis is the time taken and y-axis is the number of inputs. Okay, so the graph would be something like this. So irrespective of the number of inputs, I get a constant time. Okay, so that's why it's called as constant time, where we get a straight line over here. Okay, so based on how many our inputs are there, I still get the straight line over here. So what is the time complexity involved in the constant time? So we can say O of 1. Okay, so irrespective of the number of inputs, so that the time complexity is constant. Okay, so we denote that by O of 1. Okay, so this will be the time complexity, and also space complexity will be coming up. Okay, so let's now understand the linear time. So let's say I want to search an element within this array. Okay, so I don't know what are all the elements are there. I cannot search by index, so I just need to loop across each and every element and then search for that particular element, right? So for that, the time complexity is linear, right? So based on the number of inputs, I have to go one by one and then search for the input. Let's say I want to search for the element D within this array, so I don't know where D is placed, so which index it is. So I have to go from the start, A, B, C and D. Okay, so I find this element here and then I return that. Okay, so this is the example for linear time. So how does it differ from the constant time? So this depends on the number of inputs. So if the number of inputs are more, the time taken to search for the element will be more, right? So that is the example for linear time. If I just draw the graph for that, so it would look something like this. So the graph would be linear like this. Okay, so based on number of inputs. So I hope you got the point. So the time complexity involved in linear time is O of n. Okay, so where n is the number of inputs, so based on the number of inputs, the time complexity will vary according to that. Okay, so unlike constant time where it doesn't depend on the number of inputs. Okay, so I hope you get the point. So let's now move to quadratic time. So the best example to demonstrate quadratic time is the nested for loops. Okay, so during your college times you would have experienced nested for loops, right? So where we write a for loop inside another for loop. Okay, so this is a for loop where inside that is another for loop. Okay, so this what it does is, like, let's say I have I and j, so unless j completes its whole iteration, then I increment I, so again I run j, right? So this will become the time complexity of O of n square. So if I want to talk in the context of this example where I compare two elements like a and b, a and c, a and d, so again ba, bc, bd, so all the different combinations. Okay, so if I calculate the time complexity, that would become 4 square, that is 16 comparisons I need to make, right? So that is also another example. Okay, so that is also similar to nested for loops. Okay, so the time complexity for this is going to be O of n square. Okay, so we denote that by O of n square, where n stands for the number of inputs, so it is the square of the number of inputs. Okay, so this is the time complexity, and also there is called space complexity, which we are going to discuss later. So I hope you got the point. So what is quadratic time? So if I show you the graph for this, how will it look? So if I say, so based on the number of inputs, it would go like this in a parabolic shape. Okay, the reverse parabolic shape. So as the number of inputs increases, so the time taken will also increase. Okay, so if I have like one input, so 1 square is 1. So if I have two inputs, so that so the time is 2 square, that is 4, and 3 is 9, so it keeps on going exponentially. Okay, so this is the example for this quadratic time. So let us now understand what is logarithmic time. So I'll just consider this array over here, which is already sorted. Okay, so you see that if I want to find a number, okay, which is inside this sorted array, so I don't have to loop across all the elements within this array. Okay, so let's say I want to find the element 4 within this array. So instead of looping across all the elements, I just search for the mid element. Okay, so you might have guessed what I'm talking about, like for example the bubble sort. Okay, so I don't have to loop across everything, so I see the mid element and check if the given number to find, is it greater than current value or lesser than that. Okay, so if it is greater than that, we eliminate all the values on the left side. Okay, so if it is lesser than that, we eliminate all the values on the right side. So we see that 4, the number which we are finding, is between 3 and 5, right? So I have eliminated half of the array itself. Okay, so I don't have to search for the left side of the numbers, so I consider this to be now the array to be searched. So now again I search the mid element, so that is 4. Okay, so now we see that we have found the number 4. Okay, so by this we achieve the time complexity of logarithmic time, which means that it based on the log time. Okay, so I hope that's clear. You can also think this of a telephone directory, where if I want to search for a particular number, okay, so whose contact, let's say that contact starts from letter n, so I just need to see the middle. Okay, and then see if n is lesser than that or greater than that, and then just keep doing the same thing unless we find that. So we don't have to go across from the start, we don't have to check from a, b, c, we just go directly to that page number and then see, right? So this is an example for the logarithmic time. So if I just draw the graph of how it looks like, so it would go something like this. Okay, so you see that it increase a little at certain point in time, and then later it becomes constant. So here you see that for the first operation I have eliminated half of the array, so that is, let's say 50% of the array. So let's say it would come here, and then another 50% of that 50%, so let's say 75%. So the remaining is 25%, right? And then 25, and half of that is around 12, right? So it becomes 12, and then becomes 6, and then 3, 2, 1, and almost it becomes constant. Okay, so this is how this logarithmic time, so this is denoted by O of log n. Okay, so you know what is log, right? So the opposite of exponential, so that is the opposite of quadratic time. Okay, so this is the operation which you can use. The only thing is the condition to be is the sorted array. If it is not sorted, then we have to start from the we have to do the linear time complexity itself, where we start from the starting of the array. So this is the logarithmic time. So I think I have covered all the time complexities. So these are the most common ones which you would face while writing any kind of algorithm or a function. So let me just give you an example if this is still not clear to you. So I have 9 boxes over here, okay. So where each and every box there is some ball present in there, okay, and it's a different color ball, okay. So you can just think of this as shelves, okay. So where in each shelf there is a different ball which is inside that, and let's say I want to check what is the color, what is the ball color in number 5, okay. I don't have to go across every single shelf. So basically these are all shelf numbers, so this represents indices in an array, right? So we go to that particular index, so or the particular shelf number, and get what is there inside that, okay. So this is the constant time. So now let us see what is linear time. So if I want to search for a particular ball, let's say I want a red color ball, so I have to loop across all the shelves, okay. So I have to check in shelf 1, shelf 2, shelf 3, and then go all the way up to 9, right? So the worst case is that it would be at the shelf number 9, okay. So I have iterated all across, so I found that in number 9. So that is an example for linear time, okay. So the example for quadratic time, let's say if I want to compare two balls, okay. So if I just say you that there is a ball which is duplicate, you need to find that, okay. So what you would do, you would see what is the ball in shelf number 1 and 2, you would compare if they are same or no, and then again same from 1 to 3, 1 to 4, 1 to 5, and again you do the same from 2 to 1, 2 to 3, 2 to 4, and then you keep doing that, okay. So basically I have to do the n, so 9 shelves, right? 9 square is 81. I have to do 81 comparisons. So that is the quadratic time. Based on a number of shelves, the time complexity is increasing, right, exponentially. So 9 square is 81. So that's why it's called as quadratic time complexity. And if I talk about logarithmic time, let's say I have numbers inside this shelves, okay, and each number is sorted, okay. So if I want to find the number, let's say 50, okay, so 50 is in which shelf, we don't have to loop across everything. So we see first what is in the middle, that is 5, and let's see let's check if 50 is less than or greater than the value which is in 5. So if it is greater than that, then we eliminate all the previous values, so 50% of the work is done, and then we do the same for this remaining shelves over here, and we check in shelf number 7 if that number is greater than or lesser than, okay. So if the number is lesser than, then we consider from 5 to 7, okay, and then do the same thing, and then check if the number is existing in 6. So if it doesn't exist, then we keep doing the same until we find the number, okay. So this is the example for logarithmic time, where we just cut down the half of the array, and then the remaining array again we still cut half of that, and then keep on going unless we find that particular element, okay. And the condition over here is everything should be sorted, otherwise you have to check one by one, okay. So this is all about time complexity, guys. So I hope you understood how exactly to deal with time complexity, and get to know in any function or anything which I will come across when I'm solving problems, where I'll just calculate what is the time and space complexity. That time you will get to know in practice how exactly we need to calculate that. So let us now understand what exactly is the space complexity. So what is space complexity? The word space itself says that it is something related to memory, right, within your system. By definition, it is a measure of memory, an algorithm or a function that needs to run based on the input size, okay. So again, the common keywords are like measure of memory this time, okay, and previously it was time, but this time it is memory, okay. So that's the only difference between time and space, and an algorithm or a function based on the input size, okay. And this is also going to be denoted as O of n, okay. So the space complexity and also time complexity as well, so there's nothing difference in them. So we just need to understand the types over here. So the types over here are of course the same, that is the constant time, linear time, and quadratic time, okay. So let's say I create a function over here that adds the number of elements within the array, okay. So let's say add sum, and this is going to take in an array itself, let's say 1 2 3, okay. So inside this I'm just going to add all the numbers, so I just want to return all the numbers, okay. So by adding them, so what I can do to calculate the sum, I can just run a for loop where each and every element will be added to that, and or also I can use the higher order array method called reduce. So there are so many methods to calculate the sum of this. So at the end of the day, we are just going to see, are we creating any extra data structure, okay. So this is very important, are we creating any kind of extra data structure. So if I want to keep track of let's say something for this array, so I just need to keep track of it. So that will take in some memory. Okay, so the space complexity of that will depend on the number of inputs, right? So we are considering that. So here we are not creating anything, like we are just dealing directly with the passed in array. So we add that, so we get a value and then return that, the sum of that array. Okay, so we are not creating any additional data structure. So the space complexity of this particular function is O of 1. Okay, so I'm not creating any additional data structure based on the number of inputs. So the time complexity of this is O of 1. Okay, so let's understand what is the linear time complexity, linear space. Okay, so space complexity, sorry, I just need to replace this with space. So this is a function which will create an array based on the number that is passed in over here. Okay, so this basically, if this function is creating an additional data structure, that is array, okay, which is initialized to an empty array. Okay, so based on the number of inputs, let's say the number of inputs is 3, so we run this for loop based on the n value. So we just keep on adding each and every element to this array, so 1 2 3, and that will get returned. Okay, so here note that we are creating this additional data structure to store all the elements within the array, and then finally we return that. Okay, so if I just pass in, let's say, any number, let's say 2, so it will, this array will be 1 2, and this is what will get returned. Okay, so I hope that's clear. So this is the only difference. So here we are creating an additional data structure, but in the constant space we are not creating any data structure. So we are just calculating something and just returning, right? So here it is depending on the number of inputs. So if I have, like, let's say 100,000, so this array will also grow based on that number. Okay, so that's why this time complexity is linear. And yeah, so this is the example for linear space complexity. So again, if I plot the graph of linear space complexity, it would be a straight line like this. Okay, where the y-axis is the number of inputs and x-axis is the time taken or the space taken. Okay, sorry, I just keep forgetting the terms time and space. So this is a space. Okay, so basically the memory inside your company, inside your computer, sorry. So based on that, it will increase based on the number of inputs. Okay, so I hope that's clear. Let's see what is the quadratic space. So the quadratic space, you know, based on the number of inputs, the space consumed or the space complexity that is being accompanied here, that is square of that. Okay, so if the number of inputs is let's say 5, so the space complexity is going to be 25. Okay, so this is an example. Let's say I want to create a 2D matrix. Okay, so let's say based on 5 by 5, so I just pass in the n, that is 5. Okay, and I create a matrix, like, you know, each and so each row will have 5, and then each column will also have 5, right? So 5 into 5 becomes 25. Okay, so let's say 25 slots it has to occupy within your memory. So based on the number of inputs, that is 5, and it is occupying 25 slots in your memory, so that is the space complexity of this. So it is the square of that, right? So 5 square is 25, so that is the space complexity, and the representation of this is O of n square, and this is space. Okay, so this is the example for quadratic space. So based on the number of inputs, it keeps on, the space keeps on growing exponentially, right? Okay, so I hope this is clear. We actually do not have the logarithmic space complexity, so that is you know, almost very rare to see like that. So let me just give you a real world example for the space complexity. Let's say I have 100 images. Okay, so where each image is 5 MB. Okay, so if I want to load all of these images at once and then display it on the screen, you would guess the what would be the space complexity. So that would be 100 into 5, that is 500 MB. So it is going to consume 500 MB of your space to display all of the images. Let's say you are showing a presentation, and if you want to load all of the images and then show, then it would take this much memory. So if you want to show one image at a time, so for that we don't have to load all the 100 images, so we can just load one image at a time. Okay, so for every image, and yeah, for every next image it has to load. Okay, so it will show the loader over there, so until the image has been loaded, right? For every image that we keep on going, it will show a loader, and then we'll have to wait unless the image has been loaded. Okay, so if I want to load all of the images at once, the space complexity would be linear time. So based on the number of inputs, so the number of images, that much space it's going to occupy. And if I want to show you the example where I display one image at a time, so that would be constant space, right? So that would just be just one image at a time, irrespective of how many ever images. So I'm just loading one image at a time, right? So I don't have to load all of the images and take 500 MB of my disk space. So that's why it is a constant space. So it depends on every image size, okay, instead of the number of images. Okay, so I hope this example was helpful in understanding the space complexity. So this is all about this video for the time and space complexities. So if you have any questions, please let me know in the comments, so I'll just try to answer them related to this topic. And if I have made any mistakes, so sorry for that. I am just new to explaining on whiteboard. So this is all about for this video. So thank you so much for watching. Make sure you like, subscribe and share this video if you found this helpful. So I'll see you guys in the next video.